Picture this, a colossal void in space, so powerful that nothing, not even light, can escape its grasp. Imagine a place where time stretches infinitely and the laws of physics as we know them cease to exist. This is the reality of black holes, the universe's most unfathomable enigmas. Shrouded in mystery and awe, these celestial giants devour everything in their path, leaving behind a silence that echoes for eternity. But what if black holes are more than just cosmic vacuum cleaners? What if these mesmerizing entities hold secrets that could reshape our understanding of time, space, and reality itself? In this video, we are diving into 25 mind-bending theories about black holes, ideas so extraordinary they just might be true. From black holes as portals to other dimensions to the possibility that they might even contain entire universes, each theory challenges everything we think we know about the cosmos. Stay with us as we unravel the mysteries of these captivating wonders and explore the mind-expanding possibilities they bring to light. Now turning to our first theory, let us explore the fascinating idea that black holes act as galactic anchors, essentially the gravitational glue holding entire galaxies together. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole, a colossal entity millions or even billions of times more massive than our Sun. These black holes exert an incredible gravitational force, influencing the motion of stars, gas, and other celestial objects within their host galaxies. Imagine the galaxy as a vast cosmic dance, with all its stars and planets spinning together in intricate orbits. The supermassive black hole sits at the very heart of this dance, its immense gravity serving as the central force that keeps everything bound and orderly. Without this gravitational centerpiece, the delicate balance of these orbits could fall apart, potentially leading to chaos within the galaxy. Recent astronomical studies even suggest that these black holes might play a critical role in determining the size and structure of galaxies. They may regulate the formation of stars by emitting energy that influences the surrounding gas clouds, ensuring that galaxies maintain their unique shapes and compositions. In this sense, black holes are not just destructive forces, they are the unseen architects shaping the cosmic neighborhoods we call home. This anchoring role highlights just how pivotal these enigmatic entities are in the grand design of the universe. But this is just the beginning. Moving forward, let us delve into a theory that challenges everything we think we know about travel and dimensions, as we explore the idea of black holes as potential wormholes to other realms. Moving forward, we arrive at a theory that feels like it is plucked straight from the pages of science fiction. The idea that black holes could function as wormholes, providing portals to other regions of the universe or perhaps even entirely different dimensions. This concept, rooted in the equations of Albert Einstein's theory of general relativity, suggests that the intense warping of spacetime around a black hole might create shortcuts through the fabric of the cosmos. These theoretical shortcuts, often called Einstein-Rosen bridges, have fueled imaginations for decades. Essentially, a wormhole would act as a tunnel, connecting two distant points in spacetime, allowing for instantaneous travel over immense distances that would otherwise take millions or billions of years to traverse. If black holes are indeed gateways to such tunnels, they could offer a revolutionary means of interstellar travel, unlocking possibilities we can scarcely imagine. However, there are significant challenges to this theory. For one, the immense gravitational forces near a black hole's event horizon, the boundary beyond which nothing can escape, would likely crush any spacecraft or object attempting to enter. Additionally, even if a wormhole does exist, it might not be stable. Scientists have hypothesized that exotic forms of matter with negative energy would be required to keep a wormhole open and traversable. As of now, such matter remains purely theoretical, and there is no experimental evidence to confirm its existence. Despite these challenges, the idea of black holes as wormholes continues to inspire scientists and futurists alike. Could it be that black holes are cosmic doorways waiting for us to unlock their secrets? While we may be far from proving or disproving this theory, it pushes the boundaries of how we view black holes, not just as destructive voids, but as potential gateways to realms we have yet to discover. Speaking of time and reality itself, let us now explore a theory that takes us into the fascinating and mind-bending domain of time travel. Now turning to the concept of time itself, we delve into a theory that challenges our fundamental understanding of reality, the possibility that black holes could enable time travel. This idea stems from the fascinating effects black holes have on spacetime, particularly near their event horizons. As predicted by the theory of general relativity, the immense gravitational pull of a black hole is so strong that it warps both space and time around it. This phenomenon, known as gravitational time dilation, means that time moves significantly slower for an object close to the event horizon compared to an observer at a safer distance. In practical terms, if someone were to remain near a black hole's event horizon for what felt like minutes to them, years or even centuries could pass for those farther away. This disparity in the passage of time introduces a tantalizing possibility. Could black holes be used to travel to the future by exploiting these extreme conditions? While the notion of forward time travel seems more achievable through such means, the prospect of traveling to the past is far more complex and riddled with paradoxes. Some theories suggest that the unique structure of spacetime around a black hole might create closed time-like curves, essentially loops where an object could theoretically return to its own past. However, such scenarios raise profound questions about causality and the very fabric of reality. For instance, the infamous grandfather paradox comes into play, challenging our understanding of how events could unfold without logical contradictions. Additionally, the intense gravitational forces and radiation near a black hole pose significant technical challenges, making any practical use of time travel through these cosmic entities seem like a distant dream. Even so, studying the time-bending effects of black holes is not just a thought experiment. It has practical implications for understanding the universe itself. Observing how time behaves in these extreme conditions helps scientists refine models of gravity and spacetime, pushing the boundaries of our knowledge. Could black holes someday unlock the secrets of time travel, opening avenues that science fiction has long envisioned? While these questions remain unanswered, they remind us of the profound and mysterious possibilities that lie within the cosmos. On that note, let us venture further and uncover how black holes might one day serve as the universe's ultimate energy source. Moving forward, we dive into the intriguing possibility that black holes could one day become the most powerful energy sources in the universe. At first glance, this idea might sound like the stuff of science fiction, but it is rooted in solid scientific theory and innovation. One of the most fascinating concepts that supports this possibility is known as the Penrose Process, named after the physicist Roger Penrose who first proposed it. This theoretical process involves extracting rotational energy from a spinning black hole. To understand how this could work, imagine a black hole surrounded by a region called the ergosphere. This is where spacetime is dragged along by the black hole's immense rotational energy, creating a dynamic environment unlike anything we encounter on Earth. According to Penrose's theory, if you could send matter into the ergosphere in just the right way, it could split into two parts. One part would fall into the black hole, while the other would escape with more energy than it originally had. This escaping matter could, in theory, be harnessed to generate energy on an almost unimaginable scale. This process essentially taps into the rotational energy of the black hole, which is immense due to its sheer mass and speed of rotation. While this idea remains in the realm of theory, its implications are staggering. A single black hole could potentially provide enough energy to power advanced civilizations, making it a game changer for interstellar exploration and survival. Of course, the technological challenges of implementing such a process are monumental. The machinery capable of safely approaching a black hole and precisely manipulating matter in the ergosphere would need to endure extreme gravitational forces and radiation levels. Still, the concept inspires fascinating questions about the future of energy in a universe where fossil fuels and solar power might one day become obsolete. Could black holes become the ultimate answer to humanity's energy needs, leading to an era of unparalleled technological advancement? Only time and continued scientific exploration will tell. As we ponder this breathtaking possibility, let us turn our attention to the idea that black holes might exist in miniature forms, opening up yet another realm of cosmic mystery. Now turning to the fascinating concept of miniature black holes, we explore the theory that these tiny cosmic entities might exist, opening up an entirely new dimension of understanding about the universe. Unlike their supermassive counterparts that reside at the centers of galaxies, miniature black holes are hypothesized to be incredibly small, potentially just a fraction of the size of an atom, yet carrying the immense mass of a mountain. Scientists speculate that these black holes could have been formed during the Big Bang or in other high-energy cosmic events, where immense pressures and temperatures allowed for their creation. What makes these tiny black holes particularly intriguing is their potential to emit what is known as Hawking radiation, a theoretical prediction made by the late physicist Stephen Hawking. This radiation occurs when quantum effects near the event horizon cause particle-antiparticle pairs to come into existence. While one particle is captured by the black hole, the other escapes, slowly stealing energy from the black hole in the process. Over time, this gradual loss of energy would lead to the black hole evaporating completely, a phenomenon that is as astonishing as it is mysterious. The evaporation of miniature black holes raises some thought-provoking questions. Could we one day detect the bursts of energy they release during their final moments? Such detections could provide profound insights into the nature of quantum mechanics and gravitational physics, bridging the gap between these two fundamental branches of science. Moreover, studying miniature black holes could help us better understand the conditions of the early universe, offering clues about how matter was distributed and how the cosmic structures we observe today came into being. While no evidence of miniature black holes has been found so far, scientists are actively searching for signs of their existence, particularly through high-energy experiments like those conducted at particle accelerators. These experiments aim to recreate the extreme conditions that might produce such phenomena, bringing us closer to verifying their presence. Even though the existence of miniature black holes remains a theoretical possibility for now, they represent the boundless curiosity and ingenuity driving humanity's quest to unravel the mysteries of the cosmos. As we marvel at these tiny yet powerful constructs, let us delve into another speculative idea: the role of black holes as cosmic seeds that might have shaped the very galaxies we see today. Now turning to the idea of black holes as cosmic seeds, we delve into a hypothesis that connects these mysterious entities to the origins of galaxies themselves. Imagine the early universe, a chaotic expanse filled with swirling gases and particles just moments after the Big Bang. Amid this primordial chaos, scientists theorize that certain regions may have become dense enough to collapse under their own gravity, forming what are called primordial black holes. Unlike the supermassive black holes we observe at the hearts of galaxies today, these were far smaller but no less significant in their influence. Their immense gravitational pull could have served as focal points, drawing in surrounding matter and triggering the formation of early galaxies. In this scenario, primordial black holes acted much like the seeds from which vast cosmic structures began to grow. The matter they attracted could have condensed into stars, star clusters, and eventually the vast spiral and elliptical galaxies we see in the universe now. This fascinating theory suggests that without these black holes, the universe's landscape might have looked starkly different. possibly lacking the intricate and beautiful arrangements of galaxies we observe today. Furthermore, the connection between black holes and galaxy formation isn't just limited to primordial times. Even in modern observations, we find supermassive black holes at the centers of nearly every large galaxy, including our own Milky Way. This apparent correlation raises questions about whether these immense black holes actively shaped their host galaxies' development or merely grew alongside them. If black holes truly played a fundamental role as cosmic seeds, understanding them could unlock answers to some of the most profound mysteries of the universe's history. Could these seeds provide a blueprint for how the cosmos evolved from a dense, hot singularity into the astonishing expanse we now inhabit? As we ponder these possibilities, let's turn our gaze to yet another speculative yet captivating concept: the idea of white holes, often imagined as the mysterious counterparts to black holes, expelling matter and energy instead of consuming it. Now turning to the speculative concept of white holes, we encounter a theory that flips our understanding of black holes on its head. Imagine an object that does the exact opposite of what a black hole is known for. Rather than consuming matter and energy, it expels them in a dramatic cosmic outflow. This is the essence of a white hole, a theoretical counterpart to black holes predicted by the same equations that describe Einstein's theory of general relativity. While black holes are regions of space from which nothing can escape, white holes are regions into which nothing can enter. Their boundaries act like a one-way gate for matter and energy. But here's where it gets even more intriguing. Some scientists hypothesize that white holes might exist as the end state of black holes. In this view, a black hole could eventually transition into a white hole after it has fully evaporated due to Hawking radiation, essentially reversing its role in the cosmos. Others argue that white holes might offer clues about what happens to the matter and information consumed by a black hole. Could it all be expelled into another region of space or even a parallel universe through a white hole? This idea ties into the concept of wormholes, potentially linking black holes and white holes as opposite ends of a cosmic tunnel. However, white holes remain purely theoretical, as we have yet to observe any direct evidence of their existence. Their extreme and specific conditions, such as their requirement for a perfectly stable and unchanging environment, make them difficult to reconcile with the chaotic nature of our universe. Still, the mere possibility of their existence challenges our understanding of time, space, and the interconnectedness of cosmic phenomena. If white holes do exist, they could provide critical insights into the life cycle of black holes and the ultimate fate of the matter they consume. With this mind-bending idea in focus, let us now venture into yet another fascinating possibility: the idea that black holes might serve as bridges to other universes in the vast multiverse. Now turning to the tantalizing concept of black holes as portals to other universes, we step into the realm of the multiverse theory. This idea suggests that our universe may not be the only one, but rather part of an inconceivably vast network of universes, each with its own unique laws of physics and realities. In this framework, black holes could serve as cosmic gateways linking these parallel universes. Scientists hypothesize that the immense gravitational forces and the mysterious singularities at the heart of black holes could create conditions where matter and information do not simply vanish, but are instead funneled into another universe altogether. Imagine for a moment, what if everything consumed by a black hole, stars, planets, entire galaxies, was not destroyed but instead transformed and ejected into an alternate universe, potentially giving rise to new worlds or even new Big Bang events. This theory gains traction from the notion that the laws of physics, including the conservation of information, might still hold true in some form, even in the extreme conditions of a black hole. It sparks the question, could our universe itself have been born from such a process, emerging from the depths of a black hole in a parent universe? While these ideas are rooted in advanced mathematics and theoretical physics, they are, as of now, impossible to test directly. The extreme nature of black holes makes them incredibly difficult to study up close, and the idea of other universes remains speculative without concrete evidence. However, the implications of such a theory are profound. If black holes do indeed connect to other universes, they could hold the key to understanding the multiverse, a concept that fundamentally reshapes our perception of existence. The thought that black holes might be more than just destructive entities, that they could be pathways to entirely new dimensions of reality, challenges the boundaries of our imagination and compels us to rethink the nature of space and time itself. As we ponder this astonishing possibility, let us continue our exploration by diving into yet another profound idea: the theory that black holes might actually be holographic projections, revealing surprising insights into the very fabric of our universe. Now turning to the intriguing theory of black holes as holographic projections, we encounter a concept that challenges our very understanding of reality. The holographic principle suggests that all the information contained within a three-dimensional space, such as a black hole, could actually be encoded on its two-dimensional surface. In simpler terms, it is like a hologram, a seemingly three-dimensional image created from a two-dimensional representation. This mind-bending idea originated from the study of black holes and attempts to solve one of physics' biggest puzzles, the black hole information paradox. If a black hole truly destroys everything it consumes, including information, it violates the fundamental law of physics that information can never be completely lost. However, the holographic principle proposes a solution. The lost information is not truly gone but rather stored on the surface of the black hole, encoded in a manner we are only beginning to hypothesize about. Think of it like this: if you were to throw a book into a black hole, the physical form of the book would vanish into the singularity, but its informational essence, every word, every letter on its pages, might still exist as a sort of imprint on the black hole's perimeter. Expanding this principle to the universe as a whole, some scientists suggest that everything we perceive as three-dimensional might, in fact, be a projection of information rooted in a two-dimensional reality. This could mean that our understanding of space and dimensions is fundamentally flawed, that the very concept of depth is an illusion created by the way this information is displayed. While this theory remains a fascinating mathematical construct, it pushes the boundaries of our comprehension, urging us to ask profound questions about what is real. Could our universe itself be a holographic projection of deeper structures we cannot yet perceive? As this theory continues to unfold in the theoretical realm, it hints at an interconnected fabric of existence where black holes are not just cosmic traps but also windows into the ultimate nature of reality. Moving forward, this notion lays the groundwork for exploring yet another captivating theory: the possibility that black holes might contain entire universes within them, offering further glimpses into the infinite potential of these mesmerizing cosmic entities. Now turning to the idea that black holes might contain entire universes within them, we dive into a theory that stretches the imagination to its limits. This concept is rooted in complex mathematics and the study of spacetime structures under extreme gravitational forces. Imagine that the immense gravitational pull of a black hole compresses matter and energy to such an extent that an entirely new spacetime could emerge within its boundaries, a universe birthed inside the singularity. According to this theory, a black hole does not merely destroy what it consumes, but instead acts as a sort of cosmic gateway, where the crushed matter and energy give rise to a separate realm of existence. To better explain this, think of black holes as cosmic seeds. Just as a seed contains all the potential for an entire tree, a black hole might harbor the conditions necessary for the formation of an entirely new universe, complete with its own laws of physics and dimensions. This idea is supported by mathematical models suggesting that once matter crosses the event horizon, it could be funneled into a singularity that has the capacity to spawn a new cosmic expanse beyond our perception. If true, this would mean that within some black holes, there could be entire realities as vast and complex as our own, each existing independently and invisible to outside observers. This brings us to the mind-bending possibility that our universe might have originated from a black hole in a parent universe, a cyclical process where universes birth other universes through black holes, creating an infinite chain of nested realities. While this theory remains firmly within the realm of speculation, it provides a tantalizing framework for rethinking the interconnectedness of existence. Could the universe we call home be just one of countless others, all tethered together through these cosmic portals? As we ponder this, we are left with an awe-inspiring vision of black holes as not merely destructive forces but creators of unimaginable new realities. With this profound notion in mind, we move forward to consider another fascinating possibility, that black holes might serve as the universe's memory, storing information about everything they consume in ways that challenge what we know about the nature of existence. Moving forward, let's consider the intriguing theory that black holes might act as the universe's ultimate memory banks, storing information about everything they consume. At first glance, this seems counterintuitive. After all, black holes are often thought of as cosmic erasers, obliterating everything that falls into them. However, according to groundbreaking ideas in theoretical physics, this might not be the case. Imagine for a moment that instead of destroying information, a black hole actually encodes it onto its event horizon, the boundary beyond which nothing can escape. This concept is tied to what scientists call the black hole information paradox, a major puzzle in modern physics. The paradox arises from the conflict between two fundamental principles: the idea that information cannot be destroyed, as dictated by the laws of quantum mechanics, and the seemingly annihilating nature of black holes as described in general relativity. So where does this information go? One leading theory suggests that it is preserved in a two-dimensional form on the event horizon itself, like data etched onto a cosmic hard drive. This means that, theoretically, the intricate details of everything that has ever fallen into the black hole, from collapsing stars to stray particles of gas, could still exist in some encoded form. To grasp this, think of a black hole as a vast library, but one where the books are written in a language so complex that we have yet to decipher it. This idea has profound implications for our understanding of reality, as it challenges the way we think about the preservation of information and the very fabric of existence. Researchers are exploring whether this encoded information might eventually be retrievable, possibly through the radiation a black hole emits as it slowly evaporates, a process known as Hawking radiation. However, the truth remains elusive as scientists continue to delve deeper into the mystery. While we may not have definitive answers yet, the notion of black holes as memory keepers opens up fascinating avenues for understanding not just how black holes work, but also how the universe itself preserves its history. With this thought-provoking idea fresh in our minds, we now turn to another cosmic enigma: how black holes might explain the puzzling silence of the universe and their potential role in the Fermi paradox. Now turning to the Fermi paradox, let us explore how black holes might hold clues to one of the greatest mysteries in the universe: the apparent silence from extraterrestrial civilizations. The Fermi paradox stems from a simple yet profound question. If the universe is so vast, filled with billions of galaxies and countless potentially habitable planets, then where is everyone? Why have we not detected signs of intelligent life beyond Earth? One intriguing theory suggests that advanced civilizations may be far more resourceful and ingenious than we can currently fathom, potentially utilizing black holes as a means of energy generation or even as strategic hideouts. Imagine a civilization so advanced that it learns to exploit the immense power of a black hole. By harnessing its energy, such as through the process of accretion where matter spirals into the black hole at incredibly high velocities, they would have access to a nearly limitless source of power. This concept, often referred to as a Dyson sphere but on a galactic scale, could allow these civilizations to meet their energy needs without relying on starlight or conventional resources. But what if some civilizations seek not energy but concealment? Black holes, with their extreme gravitational pull and event horizons that trap everything within, could theoretically serve as cosmic cloaking devices. Any signals or traces of their existence would be nearly impossible to detect against the backdrop of a black hole's consuming nature. This idea may help explain why we have yet to uncover evidence of extraterrestrial life. They might be intentionally keeping themselves hidden, perhaps out of caution or fear of unknown dangers in the cosmic neighborhood. Alternatively, black holes might serve as gateways or portals to other parts of the universe, as some theories suggest, allowing civilizations to migrate to regions of space that are entirely beyond our observational reach. While these ideas remain speculative, they offer compelling perspectives on how black holes could intersect with the Fermi paradox. Could it be that the key to understanding the cosmic silence lies in the darkness of black holes? As we ponder these possibilities, our next exploration delves into the notion that primordial black holes might hold the secret to the universe's invisible matter, also known as dark matter. Moving forward, let us explore the fascinating idea that primordial black holes might be the key to understanding dark matter, the mysterious substance that makes up about 85% of the universe's total mass. Dark matter does not emit, absorb, or reflect light, making it completely invisible and detectable only through its gravitational effects on visible matter. For decades, scientists have been trying to solve the puzzle of what dark matter actually is, and primordial black holes represent one of the most intriguing candidates. These black holes are thought to have formed in the very early universe, mere moments after the Big Bang, when extreme density fluctuations could have caused certain regions to collapse into black holes. If primordial black holes do exist, they could explain at least part of the unseen mass that we attribute to dark matter. Unlike stars or gases, these black holes would not emit any light, aligning with the elusive nature of dark matter. The implications of this idea are profound, as it would reshape our understanding of both the formation of our universe and the role of black holes within it. Scientists are currently searching for evidence to either confirm or rule out this theory. For example, they are investigating gravitational lensing events, where the massive gravitational pull of these primordial black holes could bend light from distant stars. Additionally, researchers are examining cosmic background radiation and studying the distribution of matter throughout the universe to find traces of these ancient objects. The detection of primordial black holes as dark matter would not only solve a major cosmic mystery, but also open up new questions about the nature of black holes themselves and their relationship with the universe at large. Could primordial black holes really be the hidden architects of the invisible skeleton that holds galaxies together? With this compelling thought, we now turn to the next theory, which delves into the enigmatic role of black hole singularities and their potential connection to the very origins of our universe. As the next chapter of our journey unfolds, we delve into the intriguing theory that black hole singularities might hold the key to understanding the origins of our universe. A singularity found at the very heart of a black hole is a point where gravity becomes infinite, space-time curves infinitely, and the known laws of physics break down. This extreme environment is strikingly similar to the theoretical conditions of the Big Bang, the moment that birthed our universe. Scientists hypothesize that studying singularities could provide crucial insights into the earliest moments of existence, when the universe was an unimaginably hot and dense point before it began expanding. What makes this theory so fascinating is the idea that black holes might serve as natural laboratories for recreating and studying these primal conditions. By understanding how matter and energy behave under the extreme circumstances within a singularity, we could unlock secrets about the forces that shape the cosmos and potentially discover new, fundamental laws of physics. Moreover, the connection between singularities and the Big Bang raises profound questions about the cyclical nature of the universe. Could our universe itself have originated from the collapse of a previous one into a singularity? This speculation, often referred to as the Big Bounce theory, suggests that the universe might undergo infinite cycles of expansion and contraction, with black hole singularities acting as the catalysts for each new beginning. Exploring this idea opens up a realm of possibilities, not just about our universe's past but also its future. While we are far from fully understanding singularities, advancements in theoretical physics and technologies like gravitational wave detectors are bringing us closer to peeling back the layers of mystery surrounding these enigmatic points. Could singularities reveal the ultimate blueprint of existence, or are they destined to remain as elusive as the moment of creation itself? With this awe-inspiring notion in mind, we now venture forward to explore another captivating possibility: the idea that black holes might slowly evaporate over time, challenging their reputation as eternal cosmic entities. Now turning to the groundbreaking theory of black hole evaporation, we explore Stephen Hawking's revolutionary concept known as Hawking radiation. According to this theory, black holes are not the eternal cosmic prisons we once believed them to be. Instead, they slowly lose mass and energy over time through a process linked to quantum mechanics. Put simply, Hawking proposed that at the edge of a black hole, an area called the event horizon, quantum fluctuations could cause pairs of particles to spontaneously appear. Normally, these pairs would quickly annihilate each other, but near a black hole, one particle might fall inward while the other escapes. The escaping particle takes energy away from the black hole, causing it to lose mass ever so slightly. This process, while incredibly slow, suggests that over an unimaginable span of time, black holes could eventually evaporate completely. What makes this theory so remarkable is its fusion of two of the most critical frameworks in physics: quantum mechanics and general relativity. By proposing a mechanism that relies on these principles working together, Hawking's idea opened the door to a deeper understanding of how the universe operates on both the largest and smallest scales. The implications of black hole evaporation extend far beyond their eventual disappearance. If black holes truly evaporate, what happens to all the information they consume? This question touches on the infamous black hole information paradox, a puzzle that continues to challenge physicists today. Moreover, the concept of black hole evaporation forces us to think about the ultimate fate of the universe. Could the slow vanishing of black holes signify the final chapter of cosmic evolution? Or will the energy released during their evaporation play a vital role in reshaping the cosmos? While we have yet to observe Hawking radiation directly, advancements in technology and experimental physics are bringing us closer to testing this profound theory. As we unravel more of this cosmic mystery, we are reminded that even the darkest corners of the universe may hold the keys to its greatest secrets. With that thought, let us now move forward to uncover the mesmerizing phenomenon of spaghettification, one of the most extreme and fascinating processes associated with black holes. Now turning to the mesmerizing phenomenon of spaghettification, we delve into one of the most extreme and dramatic processes associated with black holes. Spaghettification, also referred to as the tidal stretching effect, occurs due to the immense gravitational forces near a black hole. Imagine an unfortunate object, perhaps a star or even a spacecraft, drifting too close to the event horizon. Here, the gravitational pull exerted by the black hole increases dramatically from one end of the object to the other. This difference in gravitational force causes the object to be stretched lengthwise, almost like pulling taffy, while simultaneously being compressed sideways. The result is an elongated, thread-like shape, hence the term spaghettification. The closer the object gets to the black hole's singularity, the stronger these tidal forces become, stretching it into thinner and thinner strands until it is eventually torn apart into its most fundamental particles. Although spaghettification may sound like pure science fiction, it is a process grounded in the laws of physics and has even been observed indirectly. For instance, astronomers have detected stars being pulled apart by the tidal forces of supermassive black holes at the centers of distant galaxies, a spectacle known as a tidal disruption event. In these events, the shredded remnants of the star form a glowing, spiraling stream of matter, some of which falls into the black hole while the rest is ejected into space. These observations not only provide a glimpse into the violent interactions between black holes and their surroundings, but also offer valuable insights into the properties of black holes themselves. Scientists have even simulated spaghettification using advanced computer models, analyzing how matter behaves under such extreme conditions. These simulations help us understand the fundamental physics at play, shedding light on the mysterious and powerful nature of black holes. While the idea of being stretched into cosmic spaghetti might seem terrifying, it also serves as a humbling reminder of the incredible forces shaping our universe. As we continue to explore these phenomena, we uncover more about the delicate balance of destruction and creation that governs the cosmos. With spaghettification vividly on our minds, let us move forward to unravel the intriguing possibility of faster-than-light travel and its fascinating connection to black holes. Moving forward, let us investigate the captivating theory that black holes might hold the key to faster-than-light travel. In the realm of science fiction, traveling faster than the speed of light often involves spaceships zipping through wormholes or warping spacetime itself. But could black holes, the enigmatic giants of the cosmos, actually make such extraordinary phenomena possible? To understand this, we must consider the way black holes distort spacetime. According to Einstein's theory of general relativity, massive objects like black holes create intense gravitational fields that warp the fabric of spacetime. This warping is so extreme near a black hole that it not only bends light but also stretches and twists spacetime in ways that defy our everyday understanding. Now, imagine if this distortion could be harnessed or manipulated. Perhaps we could use it to create a shortcut through space, theoretically allowing travel across vast cosmic distances faster than light could traverse them. Some scientists speculate that black holes might act as natural spacetime shortcuts or portals, potentially connecting distant regions of the universe. This idea is often tied to the concept of wormholes, hypothetical tunnels through spacetime predicted by Einstein's equations. If a stable wormhole could exist, it might provide a route for faster-than-light travel, effectively bending the rules of distance and time. However, there are significant challenges to this theory. For one, the intense gravitational forces near a black hole would likely crush any spacecraft or traveler attempting to approach it. Additionally, even if a wormhole could form, current theories suggest it would require an exotic form of matter with negative energy to keep it stable, something that has yet to be proven to exist. Despite these hurdles, the idea continues to intrigue physicists and spark new lines of inquiry. Researchers are exploring mathematical models and simulations to study how spacetime might behave under the extreme conditions near a black hole. These studies aim to uncover whether phenomena like faster-than-light travel could ever move from theoretical speculation to practical possibility. While the notion remains firmly in the realm of theory, it serves as a tantalizing reminder of how much there is to learn about black holes and the universe they inhabit. With this thought-provoking possibility fresh in our minds, let us now turn our attention to the enigmatic relativistic jets and the mysteries they unveil about black holes and their surrounding environments. Now turning to the fascinating phenomenon of relativistic jets, we dive into one of the most mysterious and dynamic features associated with black holes. Unlike the common perception of black holes as cosmic vacuum cleaners that consume everything in their vicinity, certain black holes exhibit an astonishing behavior. They eject matter in concentrated streams that travel at nearly the speed of light. These relativistic jets are among the most energetic events in the universe, stretching for thousands or even millions of light years across space. But how do these incredible jets form, and what do they reveal about the workings of black holes? Scientists believe that relativistic jets are powered by the intense gravitational and magnetic forces surrounding a spinning black hole. When a black hole pulls in matter from its surroundings, this material forms an accretion disk, a spinning, superheated ring of gas and dust spiraling toward the event horizon. As the material in the accretion disk churns and collides, it generates immense amounts of energy and creates powerful magnetic fields. These magnetic fields can twist and align, funneling some of the infalling matter away from the black hole and accelerating it outward at near light speeds. Interestingly, the jets do not emerge from within the black hole itself, but rather from the regions just outside its event horizon, where these magnetic and energetic forces dominate. Observations of relativistic jets have revealed extraordinary details about their impact on the surrounding environment. As these jets penetrate the interstellar medium, they heat up gas, trigger shock waves, and sometimes even ignite star formation in nearby regions. In other cases, the immense energy carried by the jets can suppress star formation by pushing gas and dust away, altering the evolution of entire galaxies. These opposing effects highlight the dual role that black holes play in shaping their cosmic neighborhoods. Despite the progress in understanding relativistic jets, many questions remain unanswered. For example, what determines the direction and intensity of a jet? And why do some black holes produce jets while others remain quiet? Researchers are actively studying these phenomena using advanced telescopes, such as radio observatories that can capture the faint signals emitted by these jets as they traverse space. By piecing together these observations, scientists hope to unlock the secrets of relativistic jets and further unravel the deep connection between black holes and their environments. With this awe-inspiring insight into the forces at play near black holes, we now shift our focus to the intriguing theory of black holes as cosmic recycling centers and the transformative role they might play in the universe's grand cycle of creation and destruction. Moving forward, we delve into an intriguing idea: black holes as cosmic recycling centers. While these celestial giants are often associated with destruction, devouring anything that falls within their reach, some theories suggest a more constructive role. What if black holes are not just endpoints for matter, but also participants in a grand cosmic cycle of renewal? The concept here is that when black holes consume matter, the extreme conditions near the singularity, where density and gravity reach unimaginable levels, might break down that matter into its most fundamental particles. These particles could then potentially be reintroduced to the universe through processes we do not yet fully understand, possibly contributing to the formation of new stars, planets, or even galaxies over cosmic timescales. This theory paints black holes as more than cosmic voids. They become engines of transformation, playing an essential role in recycling the building blocks of existence. One of the key mechanisms often discussed in this context is the role of Hawking radiation. According to this groundbreaking theory proposed by the physicist Stephen Hawking, black holes slowly lose mass over time by emitting tiny particles, effectively evaporating as they release this energy back into the universe. As the black hole diminishes, it is conceivable that the energy and particles emitted could serve as raw materials for new structures in space, feeding into the larger cycle of cosmic evolution. Although this idea is still highly speculative, it aligns with the principle that in the universe, nothing is ever truly wasted. Observations of phenomena like relativistic jets further support the notion of black holes having an outwardly active role, as these jets eject matter and energy across vast distances, interacting with and sometimes even reshaping their surroundings. Could this behavior be another piece of the cosmic recycling puzzle? Scientists are exploring whether black holes, through their various interactions with the universe, might redistribute and repurpose matter and energy in ways that contribute to cosmic balance. If proven true, this theory could fundamentally change our perception of black holes, shifting the narrative from pure destruction to one of rebirth and renewal. So, as we ponder the possibility of black holes as recyclers of the cosmos, we now turn our attention to another thought-provoking hypothesis, the idea that black holes may evolve over time, potentially unlocking new physics we have yet to discover. Now turning to the concept of evolving black holes, we encounter a hypothesis that could revolutionize our understanding of these enigmatic entities. Imagine if black holes, far from being static and unchanging, actually grow more complex over time. This idea suggests that black holes may undergo transformations influenced by the matter and energy they consume, as well as interactions with their environment. Such changes could alter their internal structure, potentially giving rise to phenomena that push the boundaries of known physics. Scientists speculate that as black holes evolve, they might develop new properties or behaviors, revealing insights into dimensions of reality we have yet to explore. One possibility is that older, more massive black holes could exhibit unique traits, perhaps even acting as catalysts for unseen cosmic processes. There is also the tantalizing thought that as black holes evolve their event horizons, the point beyond which nothing can escape might change in ways that allow us to probe deeper into their mysterious nature. These shifts could help explain some of the more puzzling observations in astrophysics, such as variations in the intensity of relativistic jets or unexpected patterns in surrounding gravitational waves. While much of this remains theoretical, the notion that black holes are dynamic entities opens the door to exciting possibilities. Could their evolution unlock secrets that bridge the gap between quantum mechanics and general relativity? As we consider the transformative potential of evolving black holes, we turn to another fascinating role they might play: their connection to quasars, the universe's brightest beacons. Now turning to the role of black holes in quasars, we delve into a phenomenon that produces some of the most luminous and awe-inspiring sights in the universe. Quasars, often described as cosmic lighthouses, shine with an intensity that can outmatch entire galaxies, and at the heart of this brilliance lies a supermassive black hole. These black holes, millions or even billions of times more massive than the Sun, draw in surrounding matter with their immense gravitational pull. As this matter spirals inward, it forms what is known as an accretion disk, a swirling, superheated ring of gas and debris that moves at astonishing speeds. The friction and compression within this disk generate an extraordinary amount of energy, releasing radiation across the electromagnetic spectrum, from visible light to powerful X-rays. This process is what makes quasars visible from billions of light-years away, allowing us to peer deep into the early universe. Beyond their radiant display, quasars also offer clues about the growth and evolution of galaxies. Scientists believe that these intense outbursts of energy can influence star formation, regulate gas flows, and even shape the structure of their host galaxies. By studying quasars, we gain insight into how black holes interact with their cosmic surroundings, shedding light on the mechanisms that govern the universe's most extreme environments. As we marvel at the power of quasars, let us journey further into the connection between black holes and another mysterious phenomenon: gamma-ray bursts, the universe's most energetic explosions. Now turning to the connection between black holes and gamma-ray bursts, we enter the realm of the universe's most energetic and fleeting explosions. Gamma-ray bursts, often lasting only a few seconds to a few minutes, release more energy in that brief span than our Sun will produce over its entire lifetime. Scientists believe these extraordinary events are linked to the dramatic deaths of massive stars and the formation of black holes. When a massive star exhausts its nuclear fuel, its core collapses under the pull of gravity, potentially forming a black hole. During this collapse, jets of particles can be launched outward at nearly the speed of light, generating intense bursts of gamma rays that travel vast cosmic distances. These jets are so powerful that they can pierce through the outer layers of the collapsing star and emit radiation visible billions of light years away. Alternatively, gamma-ray bursts may also result from the collision and merger of two neutron stars or a neutron star with a black hole, producing a similar but shorter-lived burst of energy. These cataclysmic events are not only mesmerizing but also valuable tools for understanding the universe. By studying gamma-ray bursts, astronomers can probe conditions in the early universe, trace the formation of black holes, and uncover the properties of extreme matter. Such phenomena underscore the sheer power of black holes and their ability to influence events on a cosmic scale. As we ponder the breathtaking forces behind gamma-ray bursts, let us shift our gaze to another intriguing aspect of black holes: their shape and whether they truly conform to the perfect spheres depicted in many illustrations. Now turning to the shape of black holes, we confront one of the most fundamental yet complex questions in astrophysics. Are black holes perfectly spherical, or could their shape vary under certain conditions? In their simplest form, black holes are often described as spherical objects, as this is how they appear in a static, non-rotating state according to the equations of general relativity. However, reality might paint a far more dynamic picture. When a black hole spins, as most are believed to, its rotation distorts its shape, causing it to bulge slightly at the equator and flatten at the poles. This phenomenon, known as oblateness, is a direct result of the immense rotational forces acting on the black hole's structure. The faster the spin, the more pronounced this effect becomes. Surrounding matter, such as gas, dust, or even other celestial bodies, can further influence a black hole's shape. Interactions with this matter might create asymmetries or even temporary deformations in the event horizon, the boundary beyond which nothing can escape. Additionally, theoretical models suggest that extreme scenarios, like black holes in binary systems or those affected by intense gravitational waves, could lead to even more unusual geometric configurations. Understanding the precise shape of black holes is more than a matter of curiosity. It could provide critical insights into their spin rates, mass, and properties, as well as the dynamics of the material around them. By studying black hole geometry, scientists can refine their understanding of the fundamental laws governing the universe and perhaps uncover entirely new physics. With this in mind, let us move forward to explore how gravitational waves offer an extraordinary tool to detect and study these enigmatic cosmic entities. Now turning to the detection of black holes with gravitational waves, we delve into a revolutionary method that has transformed our understanding of the cosmos. Gravitational waves are ripples in space-time, predicted by Einstein's theory of general relativity, and they offer a new window into the universe. These waves are produced by extreme cosmic events, such as the collision of black holes or neutron stars, sending out distortions that can be detected over vast distances. When two black holes merge, they release an enormous surge of energy in the form of gravitational waves, creating signals that can be picked up by highly sensitive instruments like the Laser Interferometer Gravitational Wave Observatory. These signals allow scientists to confirm the existence of binary black hole systems and to measure their properties such as mass and spin. The first direct detection of gravitational waves in the year 2016 marked a historic breakthrough, as it not only validated Einstein's predictions but also provided the first observational evidence of black hole mergers. Since then, numerous additional detections have unveiled a treasure trove of information about these enigmatic entities. Gravitational waves are unique because they carry information from regions of space and time that are otherwise inaccessible, allowing researchers to study black holes in ways that were previously impossible. By analyzing these waves, scientists can probe the dynamics of the most extreme environments in the universe and test fundamental physics under conditions that cannot be replicated on Earth. This groundbreaking technology has opened up an entirely new field of study. giving us an unprecedented look at the invisible yet powerful forces shaping the cosmos. With this remarkable tool in mind, let us now contemplate the profound role black holes might play in the ultimate fate of the universe. With the next phase of the journey in sight, we turn to the profound question of how black holes might influence the ultimate destiny of the universe. These cosmic giants, with their immense gravitational pull and enigmatic nature, are not just mysterious phenomena but potentially key players in determining how everything we know might come to an end. One possibility comes in the form of the Big Freeze, a scenario where the universe continues to expand indefinitely. As black holes slowly evaporate through a process known as Hawking radiation, they would release their energy back into the cosmos over unimaginably long timescales. This steady loss of energy could lead to a cold and dark universe where all matter is scattered and black holes themselves disappear into nothingness, leaving behind a barren expanse. Then there is the Big Crunch, a contrasting idea in which the universe's expansion halts and reverses, causing all matter to collapse back into a singular point. In this scenario, black holes could play a significant role as they merge and grow, contributing to the cascade of gravitational forces that pulls everything inward. Alternatively, some theories suggest the possibility of the Big Rip, a dramatic end where the universe's expansion accelerates to the point that even the fabric of space-time is torn apart. Here, black holes could meet a violent demise as the accelerated expansion overwhelms even their colossal gravitational strength, ripping them apart along with galaxies, stars, and atomic particles. Each of these scenarios paints a strikingly different vision of the end, yet black holes remain central to all of them, showcasing their profound impact on the fate of the cosmos. What makes these theories so captivating is not just their apocalyptic implications, but the way they challenge our understanding of time, space, and existence itself. While much remains uncertain, one thing is clear: black holes are not just silent observers of cosmic history but active participants in its grand finale. Now turning to the expanded possibilities surrounding time travel, black holes offer a unique portal into the fabric of time itself. Their immense gravitational pull creates an effect known as time dilation, where time moves slower near the black hole compared to areas farther away. This phenomenon has been observed and even measured in less extreme environments, like near Earth's gravitational field. But near a black hole, the effect is magnified to a staggering degree. If we could harness or navigate the space around a black hole without crossing the event horizon, we might be able to exploit this extreme time dilation to travel into the future. Imagine a spacecraft orbiting a black hole's event horizon for what feels like just a few years to its crew, only to return to find that centuries or even millennia have passed for the rest of the universe. This brings us to the revolutionary implications such control over time could have for physics. Understanding and perhaps even utilizing black holes for temporal manipulation could open unprecedented doors for science and technology, allowing humanity to study long-term cosmic phenomena in real time or preserve civilizations' knowledge far into the future. But with these advancements come profound ethical and philosophical questions. If time travel to the future became possible, what responsibilities would we have toward those we leave behind? Could humanity's pursuit of such technologies destabilize societies or challenge the very nature of our timeline? Beyond practical concerns, this theoretical technology raises deep existential questions about our relationship with time itself and whether we should embrace such power. While time travel through black holes remains speculative, exploring these possibilities pushes the boundaries of scientific imagination and challenges us to reflect on the immense responsibility that comes with unraveling the mysteries of time. Moving forward, let us now dive into the intriguing notion of black holes forming connections to entirely different universes. Moving forward, the concept of black holes serving as gateways to alternate universes takes us to the frontier of theoretical physics. While this might sound like science fiction, certain mathematical models suggest it could be possible. The idea stems from the solutions to Einstein's equations of general relativity, which not only allow for the existence of black holes but also hint at possibilities like wormholes, hypothetical tunnels in spacetime that could link disparate regions of our universe or even entirely different universes. To test these ideas, scientists are turning to advanced simulations and observational data. For example, researchers are examining the energy signatures and gravitational waves emitted during black hole mergers, as these events might provide subtle clues about the existence of hidden pathways or dimensions. Additionally, physicists are exploring the concept of exotic matter, a theoretical form of matter with negative energy density that could stabilize such connections and prevent them from collapsing. If evidence of exotic matter or unusual spacetime behavior near black holes were found, it could lend credibility to the idea of inter-universal links. Beyond the realm of theory, advancements in quantum mechanics are also intersecting with this topic. Some scientists propose that black holes could act as quantum computers, encoding and transferring information across different regions of spacetime. This might mean that instead of losing the information that falls into them, black holes could funnel it elsewhere, perhaps even into another universe. These investigations remain highly speculative, but they push the limits of our understanding and inspire new approaches to probing the nature of reality. However, the notion of venturing into or even observing another universe raises profound challenges. Could the physics of another universe differ so drastically that survival or meaningful communication would be impossible? What ethical considerations arise from potentially influencing or disrupting an entirely separate realm? As these questions fuel the imagination, they also remind us of the delicate balance between discovery and responsibility. With this in mind, let us now shift our focus to the jaw-dropping hypothesis that black holes might contain entire universes within them, offering yet another layer of complexity to these cosmic enigmas. Now turning to the idea that black holes might contain entire universes within them, we dive into a concept that could fundamentally reshape our understanding of cosmology and the nature of existence itself. This theory suggests that when matter is compressed into a singularity, the infinitely dense point at the center of a black hole, it could create conditions similar to those of the Big Bang, effectively birthing a new universe. Imagine a scenario where the immense gravitational forces within a black hole trigger a new expansion of space-time with its own distinct physical laws and constants. This means that every black hole in our universe could be a gateway to another universe, and conversely, our own universe might exist within a black hole located in a larger cosmological framework. Connecting this to real-world physics, some researchers are exploring the possibility that the properties of our universe, such as the specific values of fundamental constants like the speed of light or gravitational strength, could be influenced by processes occurring inside a parent black hole. This notion ties in with the concept of cosmic natural selection, where universes that foster black hole formation might proliferate similar to living organisms passing on advantageous traits. While experimental evidence for such ideas remains elusive, theoretical studies are making strides in connecting black hole physics with broader cosmological principles. For instance, simulations of quantum gravity and spacetime singularities suggest that the violent conditions within black holes might not signify an end point, but rather the threshold of a new reality on the other side. This could explain why our universe appears so finely tuned for life, because it was shaped by the specific conditions of a black hole that gave rise to it. Exploring nested universe theories challenges us to rethink the boundaries of reality and forces us to confront questions that extend far beyond the scope of traditional physics. Are we part of an endless chain of universes, each spawning the next through the mechanism of black holes? And if so, could we ever develop the tools or knowledge to peer into these hidden realms? As we grapple with these profound possibilities, we are reminded of just how much our understanding of the cosmos is still in its infancy. Moving forward, let us now examine the provocative idea that black holes might serve as the universe's ultimate memory banks, preserving information about all they consume in ways that defy conventional logic. Moving forward, let us delve into the intriguing realm of singularities, the enigmatic cores of black holes where matter is believed to collapse into infinite density and space-time itself breaks down. Singularity behavior remains one of the most perplexing challenges in modern physics, as our current understanding, dominated by Einstein's general relativity, struggles to describe these extreme conditions. However, cutting-edge research is paving the way for potential breakthroughs that could eventually demystify these cosmic enigmas. One promising avenue lies in the field of quantum gravity, which seeks to merge quantum mechanics with general relativity. Scientists are exploring theories like loop quantum gravity and string theory to explain how space-time may behave at the smallest scales near a singularity. These models suggest that space-time might not infinitely collapse but could instead stabilize into a quantum structure, effectively resolving the paradox of infinite density. Another intriguing concept is the idea that singularities might not be true points of no return, but instead transition zones into entirely new states of existence. For example, some theoretical models propose that what we perceive as a singularity could be a bridge to another form of space-time, potentially connected to other regions of the universe or even alternate realities. Researchers are also utilizing advanced computer simulations to model the intense gravitational and quantum forces near singularities. These simulations aim to recreate the complex interactions within black holes, offering insights into how matter and energy behave in these extreme environments. Such studies have begun to reveal patterns that might point to previously unknown physical laws governing the universe at its most fundamental level. Breakthroughs in this area could address some of the most profound questions in physics. What happens to information consumed by black holes? Can singularities truly destroy the fabric of reality, or do they encode clues to its deeper structure? Some scientists even hypothesize that understanding singularities might unlock entirely new technologies or reveal hidden dimensions of reality. As these theoretical models evolve, they not only bring us closer to understanding singularities, but also challenge the very foundations of how we perceive the universe. And as we push the boundaries of our knowledge, we must also confront the humbling realization that singularities represent a frontier where science meets the unknown. With these possibilities in mind, let us now turn to the dramatic question of black holes and spaghettification, a captivating process that reflects the sheer violence and awe-inspiring power of these cosmic phenomena. Now turning to the fascinating task of simulating black hole shapes, scientists are using advanced computational models and cutting-edge telescopes to unravel the intricate geometries of these cosmic giants. Despite the popular belief that black holes are perfectly spherical, their true shapes can vary depending on factors such as rotation, mass, and the influence of nearby matter. For instance, a rapidly spinning black hole may flatten slightly at the poles, forming what is known as an oblate spheroid. Observing and understanding these variations requires incredibly precise techniques. One groundbreaking approach involves the use of gravitational wave data captured by observatories. As black holes merge, they generate ripples in space-time, and by analyzing these signals, researchers can infer critical details about their shapes and characteristics. Similarly, radio telescopes, like the ones used by the Event Horizon Telescope, have provided the first ever images of black hole shadows. Through these images, scientists can study the surrounding accretion disks and deduce subtle clues about the black hole's geometry. Computer simulations also play a vital role in this field. By inputting data about a black hole's spin rate, mass, and surrounding environment, researchers create detailed models that mimic real-world conditions. These simulations allow scientists to test how black holes would appear under different circumstances and predict how their shapes might evolve over time. Such studies are not just academic exercises but provide practical insights into fundamental physics, offering glimpses into phenomena like frame dragging, where the black hole's spin distorts spacetime itself. Insights from these efforts go beyond understanding black hole geometry. They could reveal new aspects of general relativity, test predictions from quantum gravity theories, and even refine our knowledge of how black holes interact with their surroundings. As simulations grow more sophisticated and telescopes become even more powerful, the quest to decode the true shapes of black holes represents an exciting frontier in astronomy, promising discoveries that may challenge or confirm our deepest assumptions about the universe. With this exploration of geometry complete, let us now move to the awe-inspiring topic of the role black holes play in powering quasars, an extraordinary phenomenon that illuminates the farthest reaches of the cosmos. As we draw this cosmic journey to a close, the 25 theories we have explored shine a light on the vast, mind-bending possibilities black holes present. From their role as galactic anchors and potential portals to other dimensions to their mysterious connection to the multiverse, these enigmatic entities challenge us to rethink the very fabric of reality. They hold clues about the origins of the universe, the nature of time and space, and even the ultimate fate of existence itself. Each theory is a reminder of how much we have yet to uncover, urging humanity to keep pushing the boundaries of science, curiosity, and imagination. Black holes are not just distant, untouchable phenomena. They are keys to understanding some of the universe's deepest mysteries. As we continue to study them, who knows what groundbreaking discoveries await us? Could they bridge gaps between science and science fiction? Could they redefine what we know about life, energy, and the cosmos? The questions are as limitless as the universe itself. So, what do you think? Which theory fascinates you the most? Or perhaps you have a theory of your own? Share your thoughts in the comments below. We'd love to hear them. And if exploring the vast mysteries of space excites you as much as it excites us, make sure to like this video, hit the subscribe button, and turn on notifications to join us for more mind-blowing journeys into the unknown. Until next time, keep looking up and stay curious.